Hi, my name is Nathaniel Frizzell. I'm an assistant professor at the University of Scranton, lead principal investigator of the Personal Space Weather Station project, leader and founder of the HamSCI community, and amateur radio station W2NAF. Today I'm going to talk about the HamSCI distributed array of small instruments Personal Space Weather Station, architecture and current status. This is a highly collaborative project, and I would like to acknowledge all of my co-authors and many others who have made this possible. What is a Personal Space Weather Station? The HamSCI Personal Space Weather Station, or PSWS, is a multi-instrument, ground-based device designed to observe space weather effects both as a single-point measurement and as part of a larger distributed network. It is personal because it is being designed such that an individual should be able to purchase one and operate it in their own backyard. In addition, the Personal Space Weather Station design takes into account the needs of professional researchers who might want to deploy these devices for their own specific purposes. The Personal Space Weather Station is being developed as a collaborative project under the Ham Radio Sciences and Investigation HamSCI Collective, led by the University of Scranton with collaborators at Case Western Reserve University, the New Jersey Institute of Technology, the University of Alabama, the MIT Haystack Observatory, TAPR, and volunteers from additional universities and the amateur radio community. What is the purpose of the Personal Space Weather Station? The Personal Space Weather Station aims to support two primary groups of users: space scientists and amateur radio operators. Each of these groups have different but related needs. As space science researchers, we want to observe, characterize, and understand ionospheric variability on small temporal and spatial scales. We want to understand coupling between the neutral atmosphere, ionosphere, and magnetosphere, and we want to validate and improve models with the goals of prediction and understanding. As amateur radio operators, we want to understand and predict radio propagation to support amateur radio communications, including public emergency service operations, contesting, and DX long-distance communications. We also want to study space weather and propagation for personal edification and to contribute back to science and the radio art. What makes up a Personal Space Weather Station? At the heart of the Personal Space Weather Station is a software-defined radio receiver with frequency coverage from approximately 100 kHz to 60 MHz. This frequency range was chosen because signals in the medium and high frequency bands, 300 kHz to 30 MHz, are particularly sensitive to variations of the ionospheric state. This receiver will be able to listen for signals of opportunity and transmissions made specifically for coordinated experiments. The primary output of the SDR will be raw in-phase quadrature IQ samples, which can then be derived into a variety of data products. This includes snapshots of the entire high-frequency radio spectrum, Doppler shift measurements of signals received from standard stations such as WWV and CHU, oblique ionograms from ionosons of opportunity, decodes of digital amateur radio signals including FT8, the weak signal propagation reporter whisper mode, and Morse code which can be sent to the reverse beacon network or RBN. These SDR observations can also be used to measure high-frequency band noise and detect lightning signatures. A dual-frequency Global Navigation Satellite System GNSS receiver chip will be used to serve as a highly stable frequency reference, providing precision timestamping with 10 to 100 nanosecond accuracy and provide total electron content TEC measurements. A magneto-inductive ground magnetometer will provide 3-axis magnetic field measurements at a 1-second cadence with about a 10 nanotesla resolution. A local computer will coordinate operation of all attached instruments, handle local data reduction, provide a local user interface or display, send data back to a central database, and receive commands and updates from the central control system. This system is modular, so instruments can be added or removed as needed. For instance, high-latitude users may want to add an auroral camera. Where will the Personal Space Weather Stations be deployed? Currently, the Personal Space Weather Station is funded on a DAISY Track 1 grant to develop prototypes rather than deploy a network. There is significant interest from the amateur radio community in this project, so we will be looking to encourage voluntary adoption of these devices by amateurs to create an ad hoc network. The amateur radio community is global, but is heavily weighted towards North America and Europe. Initial adoption will likely be in these regions. A number of amateurs at high latitudes, including Alaska, northern Canada, Norway, and Svalbard, have also expressed interest in this project. Low-cost and software-defined radio-based versions of the Personal Space Weather Station are being designed to help maximize adoption. To help maximize adoption, two versions of the Personal Space Weather Station are being developed: a highly flexible software-defined radio-based version and a more focused low-cost version. The software-defined radio-based version has the features that were already described: a synchronized dual-channel 0.1 to 60 MHz FPGA-based direct sampling software-defined radio, cross-polarized wideband received antennas, a dual-channel GNSS module for precision timestamping, frequency reference, and total electron content measurements. A more powerful single-board computer such as the Odroid N2 will be selected as the computer. The SDR in this version is known as the TangerineSDR and is being developed by TAPR, an amateur radio electrical engineering organization. The target cost of this system is about US $500. The low-cost version of the Personal Space Weather Station is being developed by Case Western Reserve University and the Case Amateur Radio Club W8EDU. The radio in this system is known as the Grape and has a target cost of about US $100. The Grape radio has a single channel and antenna and can measure frequency variations of received signals, such as those from high-frequency standard stations including WWV in Fort Collins, Colorado, and CHU in Ottawa, Canada. A single-frequency GNSS discipline oscillator is used as a frequency standard and for precision timestamping. An inexpensive Raspberry Pi will serve as the computer. Both the versions of the Personal Space Weather Station will use the same hardware for the ground magnetometer. Additionally, the SDR-based version will have a mode to emulate the low-cost version to allow uniform data collection across the maximum number of nodes for